Good morning. So, we are going to continue our discussion of particle adhesion to surfaces. Again, to recap, so far what we have talked about in this course are analysis of shape and size of single particles, shape distributions and particle size distributions of populations of particles. And then we started talking about some interfacial properties of particles such as surface energy, interparticulate forces and adsorption. And in the last class we started discussing particle adhesion to surfaces, and we particularly talked about the van der Waals forces of attraction and repulsion between surfaces. So, today we will continue our discussion and complete our discussion of particle adhesion to surfaces and start talking about particle to particle adhesion, which is also known as cohesion. Okay. All right. So, I mentioned in the last class that the second mode of adhesion between a particle and a surface is based on electrostatic effects, electrical fields that are built up between surfaces that are in proximity to each other, and there are again three classes of these types of forces. The first is the Coulombic force, which happens between two charged objects. The second is something called an image force, and the third is the electrostatic contact potential. Now, of the three, I am sure you are all familiar with the Coulombic forces. So, when you have two charged particles or two charged surfaces that are within a distance of each other, they set up a force between them, which can be either repulsive or attractive depending on whether the charges are the same or opposite. And so, the Coulombic force will basically, if you have a particle, let us say in a surface, and they are both charged, and if the diameter of the particle is some dp and this distance of separation is some z0, then as long as both surfaces are charged, a Coulombic force is set up between them, and the Coulombic force, if you assume that the charges are the same, will look like q squared by 4 pi epsilon 0 epsilon r times dp by 2 plus z0 the whole squared, where epsilon 0 is the permittivity of free space, epsilon r is the dielectric constant, and q is the charge on each of the surfaces, and this distance represents the distance between the centroid of the particle to the other charged surface. Now, one interesting thing here of course is that dp actually occurs in the denominator, right, as it is written. So, does that imply that Coulombic force will drop as dp squared? Not really, because this parameter q for a particle is also dependent on its size. The larger the particle, the greater will be its size. And so, from this equation you cannot just say that the Coulombic force will always scale as 1 over dp squared. In fact, the relationship between the charge on a particle and its diameter also goes approximately as diameter squared, because it is a surface area phenomenon, and in fact the actual exponent is somewhere between 2 and 3, because again in a 3-dimensional view the total charges on a particle can be distributed around the volume of the particle, right. So, so this q can go roughly as dp to the power 2 to 3, on average about 2.5. So, when you look at it that way, actually the Coulombic force will increase as particle size increases in general. Image force on the other hand is the same situation, except that one of the surfaces, typically the surface is not charged. Then can you still induce a field between them? And there is a way to do that. In fact, there is something called an image force that sets in. The idea is that this charged object sets up another charge about the same distance as this distance of separation, but inside the surface. So, this is like your image charge, and the image force then is again given by q squared by 4 pi epsilon 0, epsilon r, but now the distance of separation between the two charges is twice what it was in the earlier case, right. So, it is actually dp plus 2z0 the whole squared, because this is z0, then this image will also be set up at the same distance z0 inside your surface. So, image force is similar to a Coulombic force, except that it happens when one of the two objects is not charged, and the magnitude of the image force is about 1/4 of the magnitude of the Coulombic force. So, it is clearly weaker. So, when one of these surfaces is not charged, the force that you set up is clearly going to be weaker compared to when both are charged, and that is reflected in this equation. The third type of force that can build up when you have charged particles is this electrostatic contact potential. It is also called the electronic double layer force, and the principle behind this is when you have two particles that are adjacent to each other, particularly in a gaseous medium, the particles try to come to some kind of a dynamic equilibrium, particularly based on their Fermi level or work function. So, they keep trying to exchange electrons until they reach equilibrium between themselves. As they do this constant process of exchange of electrons to reach a Fermi equilibrium sets up a potential between these two particles, and that is called the contact potential. Vcp can be of the order of about 0.5 volts actually. So, it is fairly substantial, and this contact potential results again in a force field F contact potential, which goes roughly as this contact potential squared times dp divided by z0, where dp is now the size of the particle and z0 is the distance of separation between the two particles. And by the way, this dp is a single value when the two particles are of equal size, but when they are not, then this dp has to be substituted with a dp equivalent, which is defined as 1 over dp equivalent equals 1 over dp1 plus 1 over dp2 when you have two particles that are 1 and 2 that are of unequal sizes. Okay. So, here the trend, again the thing that when you review this material, what I really want you to focus on are the key dependencies, the parametric dependencies. You do not need to know, actually in the lectures in particle characterization the more detailed equations are given, but you are not expected to memorize them. What I really look for is that you understand the dependencies of the various forces on the critical parameters such as particle size, distance of separation, applied voltage and so on, because when you are trying to design a process, whether it is a mechanical operation or any other type of chemical process, the parameters over which you have control are things like the concentration of the slurry, the average particle size of the slurry and so on. But as you control and optimize these, you have to have an understanding of how they are going to affect the effectiveness and efficiency of the downstream process. So, just focus primarily on the exponents, so to speak, the dependencies. The equivalent of the contact potential for particles that are immersed in a liquid is the zeta potential, also known as the ionic double layer force. And the way this happens is when you have particles that are immersed in a liquid, particularly a liquid that has a high concentration of ionic constituents, the ions tend to form a cloud around each particle that is immersed in the liquid. A classic example of this is a process called CMP, chemical mechanical planarization, which is used widely in semiconductor manufacturing to polish surfaces such as silicon wafers. In a chemical mechanical planarization system, you use a slurry of particles and you use these particles to do your polishing of the surface. Now, how this polishing is done, the rate of removal of the surface by the polishing medium very much depends upon obviously two things. One is the size distribution of the particles in the slurry, and the second is how close these particles can approach the surface. The closer they can approach the surface, the more fine the polish will be. And it turns out that in a CMP slurry, the parameter that most closely affects this distribution is the zeta potential. The zeta potential is a reflection of, again, how much the particles in the slurry are attracted to each other and to the surface that they are trying to polish, and therefore it affects both. The attraction of particles to each other effectively controls the size distribution. The more attraction there is, the more the tendency for agglomeration, so the size distribution will tend towards the larger sizes. And the greater the attraction to the surface, the more closely the slurry particles can approach the surface to polish it, and therefore, essentially you get a better polish. And sometimes these can be conflicting effects, because what you really ideally want is a solution or a slurry that has high attraction to the surface but low attraction to each other. And that part of the challenge of designing a polishing slurry is to achieve this. How do you maximize the affinity of the particle to the surface that you are trying to polish while minimizing the affinity of the slurry particles to each other. And again, the zeta potential is a mechanism by which we can accomplish that. The zeta potential force, the force in this case actually has an expression that is very similar to the contact potential, except that with a couple of differences. Here we talk about a zeta of the particle multiplied by zeta of the surface. So, instead of a single VCP, we actually talk about, because a potential that develops on the particle and on the surface can be extremely different. So, we split them and talk about a zeta that develops on the particle and a zeta value that develops on the surface, and again dP divided by, in this case the critical distance is the thickness of this ionic double layer that develops. So, I mentioned that in a solution you have a particle and you essentially form this ion cloud around it. So, this the thickness of this cloud is one of the parameters that affects this force as well. In fact, from this expression, again you might quickly conclude that there is an inverse dependence on the ionic double layer thickness, but that is really not the case, because the potential is also related to this. So, again, if you actually look at this more closely and look at the effect of the thickness of this ionic cloud on each of the parameters, you will find that in effect a thicker ionic cloud results in a greater potential, which is what you would normally intuitively expect, and that is basically what happens. However, the explicit dependencies, if you look at the equations, look like this. So, in a medium in which you have zeta potential as a controlling mechanism, there are many ways in which you can affect the zeta potential, and typically controlling the pH is one method, because when you control the pH, you are controlling the level of dissolved ions in the liquid, and that has a significant influence on the zeta potential. So, one of the parameters that people vary and try to optimize in this chemical mechanical planarization type of systems is the pH value. Of course, the electrolyte concentration is another major variable, as is the size distribution of the slurry particles before you start the slurry process. I mentioned that high affinity of the particle to the surface is good because it gives you a closer polish, but there can be a downside to that as well. One of the difficulties when you do this CMP process is that the slurry particles can themselves get embedded on the surface that you are trying to polish, in which case they become a contaminant that can actually have an adverse effect on the functionality of the device that you are trying to make. So, again, ideally you want a slurry which does extremely fine polishing, but the particles do not stick on the surface, that as soon as the polishing is done the particles are removed, and that is sometimes difficult to accomplish. So, there are downstream particle removal processes that are used, typically involving ultrasonic or megasonic technology, which can actually dig out these embedded slurry particles and loosen them and then rinse them off the surface, so that you restore the surface to its pristine cleanliness level before it goes to the next step. But in general, anytime you are using a slurry polishing process for a surface which is sensitive to contaminants and impurities, you have to remember that the adhesion force has to be again optimized in such a way that you get good polishing, but at the same time you do not embed the particles too deeply or too strongly. Okay. All right, so that is the second mechanism. The third mechanism that we talked about is surface tension as a way of promoting adhesion. I am sure you are all familiar with the fact that when you are trying to improve wettability of a surface, you use a surfactant, and the reason for that is when you use a surfactant it reduces surface tension. So, surface tension is a force that develops when you have a surface and you have a particle and there is a liquid medium. Now, if the liquid medium never gets into the interface between the particle and the surface, nothing is going to happen. The particle is going to behave like the adhesion process will be similar to a dry adhesion process in the absence of a liquid medium. However, if the liquid is able to wet the interface between the particle and the surface, then surface tension based forces become an additional adhesion mechanism. And the expression for a surface tension based adhesion force is 2 pi dp gamma. Actually it is 2 pi dp gamma cos theta, where theta is the contact angle, but assuming that the contact angle is 0 and you have good spreading of the liquid on the surface, this becomes 1, and for a wetting liquid the surface tension based force can simply be written as 2 pi dp gamma, where of course gamma is the surface tension of the liquid. So, I mean surface tension based forces are fairly simple to envision, but there is a little bit of a trick here in that by reducing surface tension you make it easier for the liquid to wet the interface between the particle and the surface. But at the same time when you reduce surface tension you can see that this surface tension force also decreases, right. So, again it is a trade off. You want to optimize the surface tension in such a way that you get good wicking of the liquid or wetting of the interface between the particle and the surface, but you do not want to lower it so much that even if surface tension based adhesion happens it is too weak. So, if you plot surface tension versus surfactant concentration, the kind of curve that you typically get would look like this, where there is initially a very steep drop in the value of the surface tension as you increase the concentration of the surfactant, and then it levels off. And in fact this leveling off point is known as, anybody knows what that is called? It is called the CMC, or critical micelle concentration. Once you go above that value, further increases in the surfactant concentration are not going to result in a change in the value of the surface tension. So, typically people like to keep the surfactant concentration well below this critical micelle concentration value. Somewhere where there has been a steep drop in the surface tension, but you are not yet at the at the CMC value. So, you have to, I mean there is no hard and fast rule that it should always be set at 75% of the CMC or something like that. It's something that you need to do by trial and error. For every system that you operate, for every process that you own, the ideal surfactant concentration / liquid surface tension may have a different value, and you have to learn that by experimentation and so on. So, when the liquid gets in between the particle and the surface and it causes adhesion to happen, the phenomenon is called capillary bridging. Because basically a liquid bridge happens between the particle and the surface due to capillary action, and that can be a fairly strong force of adhesion. However, it gets much stronger if you then dry the surface. Then this liquid bridge that is formed as a meniscus between the particle and the surface suddenly gets transformed into a solid bridge. So, it almost becomes like the other mechanism I was mentioning earlier, the physical entrapment mechanism. The particle is now physically attached to the surface. So, as you can imagine, the adhesion forces will be orders of magnitude stronger. If you are worried about adhesion, this is something you do not want to happen. Again, coming back to your home as an example, when you have a dirty dish, you know that you should keep it wet in order to make it more cleanable. But then if you make it wet and then you let it dry, it becomes much harder to clean because of this phenomenon of solid bridging. So, the point is that if you have a surface that you are trying to keep clean, it is a good idea to keep it wet, because although surface tension based forces can increase, all the other forces decrease. As we have seen before, electrostatic forces will drop because static charges dissipate in water. The van der Waals forces will drop quickly. So, in general, keeping a surface wet is the right thing to do, but then you have to make sure that all the particles on the surface are removed before you allow the surface to dry. Otherwise, you could actually make the situation a lot worse than it was to begin with, because the adhesion force can now be much stronger than it was before you introduce the liquid on the surface. So, you have to kind of be careful with this phenomena of capillary bridging, and which then becomes solid bridging when drying happens. Again, there may be cases where you want to promote adhesion of surface of the particles to the surface, in which case actually this conversion of a liquid bridge to a solid bridge is a good thing, but most of the time it is not. You have to kind of keep your eye on it and make sure that it does not happen. Another type of adhesion force that we listed last time is hydrophobic hydrophilic forces. What do we mean by that? This is again particularly important when you have particles suspended in a liquid. So, let us say that you have a beaker with water, and you have two particles in here which are hydrophobic in nature. Water, of course, is hydrophilic. In this situation, do you think the two particles will have a tendency to attract each other, or do you think they will repel each other? How many people think that two hydrophobic particles suspended in a hydrophilic liquid will attract each other? And how many think they will repel? And how many have no opinion? No, but seriously, why do you think they will attract? Somebody wants to explain? You have two hydrophobic particles sitting in a hydrophilic liquid. You can almost look at it like two positively charged particles sitting in a neutral medium. They will repel, right? Now, when you have two hydrophobic particles that are sitting in a hydrophilic medium, your expectation based on the electrical analogy would be they would repel, right? But they do not, they actually attract. And the reason is again thermodynamics. So, the system is trying to come to equilibrium. Now, what is the lowest free energy situation for this system? The hydrophobic particle does not like the hydrophilic molecule around it, tries to push it away, and this particle does the same thing. So, they keep pushing hydrophilic molecules away, eventually they are going to find a way to each other, right. So, two hydrophobic molecules or particles in a hydrophilic liquid will attract. How about if you have, let us say that two particles in water that are hydrophilic, then what do you think they will do? They are both hydrophilic and they are sitting in water as a medium. Will they attract or repel? Well, you know that water is the most hydrophilic because it is hydro. So, the answer is they will repel also. They will repel in this case, because even though they are both hydrophilic, water is more hydrophilic than any other known substance. So, as long as these hydrophilic particles are suspended in water, there will always be a tendency for them to prefer attaching themselves to a water molecule rather than to each other. However, if it was not water, but simply some other liquid which has a lower hydrophilicity than water, then the comment is right that we will have to look at the relative hydrophobicity and the relative hydrophilicity of the immersed particles and the liquid in which they are suspended. So, in practically every case we can predict whether particles in suspension have a tendency to attract each other or repel each other, and this is quite important because when you have particularly nanoparticles in a suspension, keeping the nanoparticles segregated is a real challenge. Again, it is not the synthesis of the nanoparticles, it is not the processing of the nanoparticles, it is the storage and transport of nanoparticles that is truly challenging. And the biggest challenge is keeping the nanoparticles as nanoparticles, not letting them agglomerate and so on. And so, the way you do that, for example, if you know that your nanoparticles are hydrophobic, you do not really want to suspend them in a hydrophilic liquid because they will have a tendency to agglomerate. So, you will try to suspend them in a solvent which is more hydrophobic than either particle. And similarly, if you have hydrophilic particles, many metal nanoparticles are hydrophilic in nature, then you probably want to suspend them in water because they will repel each other. But the other way that you can affect this attraction versus repulsion is by using surfactants as a coating. A technique that is very commonly used in dispersion of nanoparticles is to coat the surface with a, for example, particularly if you have hydrophobic particles and you want to store them in water or some hydrophilic medium, because it is the most convenient way. Solvents are very difficult to use, they are very difficult to store, they are very difficult to dispose of. So, people like to use water primarily as a processing medium, but then if you have hydrophobic nanoparticles, you would be worried about them coagulating, right. So, what you do is you introduce some surfactant into the liquid which coats on the surface of the particles and turns it from being hydrophobic in nature to being hydrophilic in nature, and as soon as you do that they start repelling each other. And that is the reason why introduction of surfactants into a nanoparticle suspension is commonly employed as a technique to keep the particles well suspended in solution without this tendency to agglomerate. Okay. All right. So, I think those were the methods that we had listed as sort of, or the phenomena that we had listed as universal phenomena that affect particle adhesion to surfaces. Of course, as we mentioned in that class, there are also some specific forces of adhesion that come into play for specific types of surfaces, but we will deal with those as and when the situation arises in the remainder of the course. So, let us quickly switch over to cohesion. Now, cohesion, as I mentioned, is not fundamentally different from adhesion. The primary differentiator is you now have two particles that are trying to stick to each other rather than a particle trying to stick to a surface. Again, before we get into cohesion, are there any questions related to adhesion or any of the topics that we have covered so far that you always wanted to ask. Okay, so when we look at cohesion, first what are the things that are common to adhesion and what are the things that are different? Some of the forces are very similar. For example, the van der Waals forces of adhesion do not change much in terms of parametric dependencies when you talk about particle to surface versus particle to particle. Same thing with all the electrical forces, that particularly the Coulombic force, when you have two charged particles versus a charged particle and a charged surface, the equations are not any different, right. So, some of these fundamental interactions are no different between adhesion and cohesion, but what are the things that make cohesion unique, that requires us to study it differently from adhesion? Of course, from an application viewpoint, they have very different consequences. Particle adhesion to surfaces primarily from a mechanical operations context primarily applies to the interaction between particles in a flowing suspension and surfaces such as pipes and tubes that they come in contact with, because adhesion plays a significant role in particles getting detached from the flow field and getting attached to a surface that they come in contact with. Cohesion, on the other hand, actually has a much greater influence on particle behavior, because it can affect everything from particle storage to particle discharge to particle flow to particle collection. In particular, it affects pressure drop, and process engineers are always worried about pressure drop, because pressure drop has an immediate impact on cost of the process. The higher the pressure drop that you have to deal with, the greater is your processing cost. So, a process engineer would like always to minimize pressure drop so they can pump more fluid through with a smaller pump in a sense, and therefore the process costs less. And cohesion has an immediate effect on pumping or flowability. The more cohesive a flow, the less flowable it is. So, it requires more effort to pump it. High level of cohesion can turn a Newtonian liquid into a non-Newtonian liquid, right. And as you know, non-Newtonian liquids are much more difficult to deal with, much less predictable and controllable than a Newtonian liquid. And the biggest drawback of having significant cohesion is that liquids that are normally Newtonian become non-Newtonian as the level of cohesion increases. And again, at the extreme case, if you have particles that have highly cohesive tendencies, you can start to see solid masses moving through rather than individual particles, and as you can imagine, that can be very difficult for process equipment to handle. So, cohesion is certainly has different implications. I would say more far-ranging implications for mechanical operations compared to adhesion. So, it is important to understand cohesion also in some detail. So, the first thing we need to look at is, how does cohesion happen? What is it, a single stage process, or does it happen gradually? So, people have studied this fairly closely. What they have found is, initially you may have two particles that are separated, right. Cohesion is 0, and then as the particles start to approach each other, you can have two particles that are essentially now kind of packed together. The interface between these two particles is wetted, and there is continuity between the surfaces, and this is called the pendular state. A pendular state involves two particles that have started to come together due to cohesive effects. The next stage is that you add one more particle, and this is called the funicular stage, F-U-N-I-C-U-L-A-R. And the next stage is you add a fourth particle, and this is called the capillary stage. And then once the number exceeds 4, that is called the droplet stage of cohesion. So, these are the different degrees of cohesion. Okay, you start with no cohesion, go to the pendular state, then the funicular state, then the capillary state, and finally the droplet stage. And the cohesive force obviously increases as you go through these stages. A simple way to visualize this is, again, if you look at two adjacent particles, they form a meniscus. So you can actually draw a line from the center of the particles to where the meniscus forms. Let us say you call that some angle beta. The smaller that beta angle, the less the cohesion is between the particles, because the meniscus is confined to the center. Whereas as beta starts to approach 90, it says that the meniscus now encapsulates the entire particle. That is a very high level of cohesion. So the level of cohesion going from these states can essentially be correlated in terms of this. This is called the angle of cohesion. This beta is known as the angle of cohesion. So beta equals 0 implies this state where there is no cohesion, and as you go through these various states, beta increases towards 90 degrees. And because of that, you can actually start expressing the cohesive force in terms of this value beta. Now, when we talk about cohesion, what are the unique forces that come into play apart from the forces that we have already described when you talk about adhesion? There are three of them. The first is capillary forces, the second is viscous forces, the third is spring-like forces. And each of these has a normal component and a tangential component. So if somebody were to ask you to list all the terms involved in cohesive force, you would have to start with van der Waals forces, electrostatic forces, Zeta potential forces, hydrophilic, hydrophobic forces, plus the capillary forces, plus viscous forces, plus spring-like forces. So you can imagine that the cohesive adhesion or cohesive behavior is actually a lot more complex to deal with than simple adhesion. And also when cohesion happens, your way of dealing with the flow itself changes. When you have individual particles, you can treat the particles as a dispersed phase in a continuous phase, which is a liquid. So when you do flow modeling, you always look at multi-phase phenomena. So when you have a non-cohesive flow, the particles are discrete entities in a macroscopic continuum flow of a liquid. However, as the particles start attaching themselves to each other, then they can become like a second continuous phase, right, because they are not discrete particles anymore. So as the level of cohesion increases, the flow behavior or flow characteristic itself can turn from a discrete or dispersed phase flow to a continuous phase flow. And in terms of how you deal with it in terms of flow equations, there is clearly a significant difference between the two cases. So again, as cohesion increases, the flow becomes more difficult to characterize mathematically, because it's much easier to deal with less concentrated suspensions when the particles are behaving in a way which is not coherent. Of course, in a way that also increases the complexity, because now you have to follow the dynamics of individual particles. So the computational time required can actually increase in flows that are less cohesive. In flows that are more cohesive, you do not have to deal with individual particles, you can essentially deal with groups of particles. So in that sense, in terms of computational effort, computational time, cohesive flows are sort of easier to handle. But in terms of accuracy, in terms of your precision, your ability to predict flow, a non-cohesive flow is much easier to predict particularly in terms of the gross parameters such as pressure drop, energy consumption and so on. When we look at flows in industry, what are some of the typical cohesive flows? Well, some of the mechanical operations that you are going to be dealing with is again storage of grains in silos. You have seen these large silos, particularly in rural areas where they are storing large quantities of various grains, and then you periodically discharge them and use them for various purposes. That is a flow that quickly develops cohesivity. Whereas if you look at, for example, a system in which you are trying to make catalyst particles, right? In that particular case, you don't really want cohesion to happen. You want the individual catalyst particles to be kept separate from each other, so that each can be individually characterized, each can be individually designed and so on. So, many of the applications that you are going to be looking at in mechanical operations involve particulate laden flows. As we go through these, you have to kind of keep in mind that some of them are likely to have high levels of cohesion and some of them are likely to have low levels of cohesion, and make sure that you kind of treat them appropriately in terms of how you describe them in a flow model, in terms of how you try to derive predictions regarding their behavior and so on. All right. So, what we will do in the next class, we will take up the capillary, viscous and spring like forces in some more detail, complete our discussion of cohesion as a mechanism, and then the last part of the fundamental analysis is going to be looking at particle dynamics and transport behavior. And after that, we will be ready to jump into some actual mechanical operations and see how all of this ties into the specific processes. Any questions? Okay, so I'll see you next class.